Welcome to this class. In this class, we'll discuss about differentiation of implicit functions, and later on at the end of this lecture, we'll discuss Lagrange multiplier technique to use to find the extremum value of the function. So let us start with the implicit functions. So let us consider that we have a function in which our independent variable is x. So let me denote this. Suppose this is independent variable, and we have another variable y, which is dependent variable. So generally we write this as y as a function of, let me denote a function of x. Suppose if I can write the dependent function, the dependability of dependent variable on independent variable through some explicit form in the form of function g, then I can call this function as explicit function. But this may not be always positive, and sometimes it is possible that we can write the relation between x and y through some implicit relation. So if I have two variables x and y, the function which relates x and y can be in the form of implicit function, and which looks like f of x comma y equal to 0. So instead of writing y in the explicit form as a function of x as g of x, I can write a function of x comma y to be equal to 0. Suppose, for example, if I write a simple equation, a straight line, for example, y equals to mx plus c. So here I can write y as a function of g of x, where this g of x can be defined as some mx plus c, where this m and c are constants, right? So this is called explicit form. This is called explicit form. But suppose if I write the same equation as mx minus y plus c equals to 0, then I can call this implicit form. So this I can write as f of x comma y equal to 0. So explicit function can be represented in the implicit form, but it is not necessary that implicit function can always be represented as explicit form. So we are going to see how to differentiate this particular implicit form of the function. So we have, remember, we have x as independent variable and y to be dependent variable. So in short, y, the value of y depends on x. Now, suppose x being independent variable, suppose if I take a differentiation of this function f with respect to x, then the total derivative of this function f with respect to independent variable x can be written as df upon dx. So this is the total derivative. This is total derivative of implicit function f with respect to independent variable x. But remember here, f now we have written in the form of function of x and y both. So to write this total derivative of this function df upon dx, I need to bring in the partial differential of this function with respect to x and y. And how to go about that? So this is a total differentiation with respect to x. So I have to consider differentiation, partial differentiation of f with respect to x and y. This I can write as del f over del x, partial differentiation with respect to x into dx upon dx, but that would be 1, plus at the same time I need to consider the dependence of function f on y. So del f upon del y into, I need to multiply, because at the end we are finding total derivative with respect to x, but in this second term we have differentiated the function f with respect to y. So I need to multiply according to chain rule dy by dx, because y being a function of x, I can write dy by dx, not del y by del x, because my y value depends on x only. So I can write dy by dx. And if you look at this equation, if you look at the function form, f equal to 0, so the total derivative of this f with respect to x has to be 0. So this has to be 0. So if you solve this particular equation, what do you get here? So you get here, so if you find dy by dx to be equal to, you take this to the left hand side, you get this minus of del f over del x divided by del f over del y. So if you have a function in the implicit form as f of x comma y equal to 0, then derivative of y with respect to x can be found as minus of del f over del x, means partial differentiation of with vf with respect to x divided by partial differentiation of f with respect to y. So this we have already studied in some 12th standard or something like that, but not exactly in this form. So we would have directly differentiated implicit function with respect to x and found our answers, right? So but this can be the way in which we can find the differentiation of implicit functions. We'll look into the examples. So suppose instead of taking this x to be independent variable, someone can take this y to be independent and x to be dependent variable. So what happens? Let us see this. Now suppose we have the same function, again implicit function f of x comma y equal to 0. So this is implicit function, but in this function someone might consider that y is independent variable. Now y is independent variable and x is dependent variable. X is dependent variable. So to find the derivative of this, so I need to consider the total derivative of this function with respect to independent variable. So this is basically df over dy. So how to find again this total derivative? I need to consider this f being a function of x and y both. I need to bring in partial differentiation. So this is del f over del y into dy upon dy, which is 1, plus again the dependence of x, so del f over del x into, now I need to, as I am differentiating with respect to y, I need to take a derivative of x with respect to y according to chain rule, and look at here, x is our dependent variable and y is our independent variable, and again f equal to 0, so total derivative of this with respect to y has to be 0. So if you solve this particular equation again, so here you can find a dx over dy equals to minus of del f over del y divided by del f over del x. Now again, let me write the previous form. You have got this one, dy over dx equal to minus of del f over del x divided by del f over del y. So this was the form previously, right? Now you can correlate these two forms. Suppose instead of writing this as implicit function, you could have write this as explicit function. Some this y equal to some g of x. And suppose there exists the inverse function of this g of x, then you can always relate this dy by dx to dx by dy through this relation dx over dy, where obviously this dx over dy is not equal to 0. This condition must be satisfied. Again, here also your partial differentiation with respect to x or with respect to y should not be 0. That's fine. Okay, and if you look, suppose instead of writing this, so where did we come from? We are coming from this implicit form and we are discussing now explicit form y equal to g of x. And let us assume that there exists inverse function of this g of x. So I can correlate dy by dx and dx by dy in this form. And if you look from the implicit point of view, here you have got relations for dx by dy and dy by dx. If you look at this, these are reciprocals of each other. So that's how you relate these terms. And this is how you find the derivative of implicit functions. So let us take an example and see how it works for us. Okay, so we have taken an example. We have a relation between y and x through some implicit function, x plus e raised to y equals to 2xy. So with our usual procedure, suppose if we consider y to be dependent variable and x to be independent variable, and if we directly find the derivative, so we need to differentiate with respect to x. So if we differentiate with respect to x, what we got? So derivative of x is 1 plus derivative of e raised to y is e raised to y into dy by dx is equal to product rule. So this is 2x into dy by dx plus derivative of x is 1. This is 2y. So sort out, so list out the terms with the dy by dx to the left hand side. So you get e raised to y minus 2x times dy by dx equals to, you can take this out and you can take this 1 to the right hand side, 2y minus 1. So ultimately you have got the relation for dy by dx to be equal to 2y minus 1 divided by e raised to y minus 2x. So this you must have studied, right? So this is our usual methodology of finding derivative of implicit functions. But let us use the partial differentiation to find the derivative of y with respect to x in this implicit function. So here I can write this implicit function as f of x comma y, that is equal to, I can write this as x plus e raised to y. I'll take this 2xy to the left hand side minus 2xy, and this becomes equal to 0 now. So remember here, to write the function in implicit form, you have to write some function form f equals to 0 or some constant, because ultimately you will be taking the derivative of this f with respect to x and y, partial derivatives. So your function form should be some f equal to constant or some f equal to 0. So it's always better to write as a function f of x comma y to be equal to 0. Now, according to partial differentiation rules, so del f, if you differentiate with respect to x, del f over del x is, this is 1. So this will be treated as a constant because this involves only y terms. So here y is constant, derivative of x is 1. So this would be minus 2y. This would be minus 2y. And if you differentiate with respect to y, del f over del y, so this would be again, this x now will be treated as constant, derivative of e raised to y is e raised to y, and this x is constant again, derivative of y is 1, so this is minus of 2x, minus of 2x. And if you remember, you have got this relation dy by dx equals to minus of del f over del x divided by del f over del y. So minus of this into bracket 1 minus 2y divided by e raised to y minus 2x. So what did you get here? So dy by dx, ultimately you got this relation 2y minus 1 divided by e raised to y minus 2x. So if you look at this number 1, which you have obtained through your standard methodology, which you would have studied in standard 12th, and now you have studied the partial differentiation. If you correlate these terms, you can see that the dy by dx can easily be found by using partial differentiation. So this may involve a little bit of calculation, but this may look simplified version of this solving this problem. So you can simply find the partial derivatives of your functions with respect to your variables and easily find dy by dx in this particular function form, implicit function form. So let us take another example. So let me take another example. So example 2. So let us take this example, x raised to y plus y raised to x equals to c. Now, if you look at this example, so if you go on solving with your standard methodology, you need to differentiate this with respect to x. So how you solve with respect to x? So you need to solve this with respect to x. You have to differentiate with respect to x. So here, if you go about it, you can solve this example, but now we'll be solving this example with a partial differentiation. So again, to use this as an implicit function, let me write this f of x comma y in implicit form, x raised to y plus y raised to x minus constant equal to 0. Or you can simply put this x raised to y plus y raised to x equal to some c. It doesn't matter because c is anyway constant. Now let me find this differentiation of f with respect to x. So while taking with respect to x, y is treated as constant. So some x raised to n form. So this would be y into x raised to y minus 1. So this would be like a raised to x. So this would be y raised to x into log y, into log y. So this is it. Now del f over del y. Now x will be treated as constant. So x a raised to y. So this would be this times log x plus now x into y raised to x minus 1. And now from this, you can find your dy by dx. dy by dx is equal to minus of del f over del x. So minus of del f over del y. So this would be minus of del f over del x is your y into x raised to y minus 1 plus y raised to x into log y divided by x raised to y times log x plus x into y raised to x minus 1. So this looks very cool and easy for us to find the dy by dx if your function form is implicit, not an explicit function. You can simply find the derivative, partial derivatives with respect to your variables x and y, and you can use this simple relation and you can easily find the dy by dx term in this. So if you go about it solving directly, you have to consider this x raised to y plus y raised to x. If you differentiate with respect to, again, you'll get the same answer. But again, so in partial differentiation method, you just need to find the partial derivatives and that's it. Put it in this particular form and you are through, right? Okay, so this is all about differentiation of implicit functions. So let us move ahead and let us study the next point, which is Lagrange multiplier method. So what is Lagrange multiplier method? Lagrange multiplier method. So this method is used to find the extrema of the function, that can be maxima or minima, subjected to some constraint. So this can also be called sometimes constrained extrema. Constrained extrema in the sense we have to find the extremum value of the given function subjected to certain constraint. So let us consider that you have given a function f of x comma y comma z to extremize. You need to extremize this function f of x comma y comma z. So this function depends on variables x, y, and z subjected to you have certain constraint, subjected to constraint. So you have to find the extremum value of this function, but at the same time you must follow certain constraint, and let us take this constraint phi as a function of x comma y comma z equal to 0. So this constraint you need to follow. Okay, so when you have a function to extremize subjected to constraint phi of x comma y comma z to be equal to 0, then you can define a Lagrangian function. So you can define a Lagrangian function which will look like Lagrangian. This is L Lagrangian. Let me give a space for this. Why I will say you now. This now you can define as the original function to extremize plus some constant lambda times your constraint x comma y comma z. So this is your original function. So this is your original function to extremize. This phi of x comma z equal to 0 form. This is important. This is your constraint. This is your constraint to follow. And this lambda, this constant which we introduced, is called Lagrange multiplier. So this Lagrange multiplier is not just like a term or some constant here. It has certain physical meanings in certain physical problems. So it is not like just we introduced one number over here. Okay. So if you'll study further in some physical sense or in some physics point of view or in some application point of view, you'll get to know that this lambda has certain physical meaning to it. So, okay, let us not go into the physical details about this Lagrange multiplier. So now we have defined this Lagrangian function as the original function to extremize plus Lagrange multiplier times constraint. So if you have multiple constraints, so suppose if you have phi 1, phi 2, phi 3, and so on, so you'll need those much of Lagrange multipliers. So you'll need lambda 1, lambda 2, lambda 3, and so on. Okay, let's not worry about multiple constraints straight away. So let's have this simple version of this constraint. So if you look at the right hand side, this Lagrangian function no doubt will depend on x comma y comma z. But now you have introduced one more variable to this particular form of equation, and which is your Lagrange multiplier. You need to find the value of this Lagrange multiplier as well. So your Lagrangian will be a function of x comma y comma z, and there will be one more variable added to it, which is your Lagrange multiplier. So if you have in general n number of constraints, so you can write your Lagrange multiplier as a function of x comma y comma z, and for one constraint you need one Lagrange multiplier. Suppose if you have n constraints, you need n different Lagrange multipliers. So let me denote this as lambda 1, lambda 2, and so on up to lambda n. And now your function, this Lagrangian function, will look like this. Will be dependent on only x comma y comma z plus first Lagrange multiplier times first constraint phi 1 x comma y comma z plus second multiplier times second constraint phi 2 x comma y comma z, and so on up to the nth constraint, nth Lagrange multiplier times nth constraint phi n x comma y comma z. So this is a generalized form. So this is generalized form. So we are not going to study n constraints straight away. We'll simply look at one constraint because the logic is same, right? So how to solve about this? So why to add this Lagrange multiplier multiplied by this constraint to be followed, and how just by solving this Lagrangian function or just by finding the extremum values of this Lagrangian function, how we are able to find the extremum value of this function f of x comma y comma z. Let us look into this. Okay, so the next point we'll be discussing is this. So you have Lagrangian function x comma y comma z comma Lagrange multiplier as a function x comma y comma z plus Lagrange multiplier lambda times constraint x comma y comma z. So see, your vision is basically you have to extremize this function. So how do you extremize this function? So extremizing this function, extremizing means maximum or minimum, extremize function. So how you go about it? Find critical points first. Find critical points. So what are critical points? Critical points means where your first derivative becomes 0. So what is first derivative basically? So the first derivative is basically a slope. Suppose if you have a function in the form of f of x comma y, so your function f depends on both x comma y. So in the sense, your function f depends on a plane xy, and at certain position x comma y, you have function value, which let me denote as z. So basically z is the height and xy is the plane. So in the plane, at each point, you have a certain height assigned to your function, right? So basically, if you plot this in three-dimensional graph, your function f of x comma y will look like a surface. And we are going to extremize this. So you can correlate. Suppose if you have curve, simply curve, this curve is always written as f of x, y equal to f of x. This is our y, this is our x. If you look at this curve, let us say this is curve. And suppose you find the derivative over here. So you can see here to this top, the maximum value, to the left and to the right. To the left it is decreasing, to the right it is decreasing. So you have achieved a maximum value, and if you find the slope here, so your slope would be dy by dx to be equal to 0. So this is the condition. So the same case with minima also. So if you suppose if this function grows like this, now if you look at this particular point, so this at this point again dy by dx, so rate of change of y with respect to x becomes 0. So dy by dx equal to 0 does not only mean the maximum, it may mean the minimum. And remember here, so it cannot be the global maximum or global minimum. Global in the sense, suppose if this function is defined over range of real numbers. So you suppose if this function is coming from this side like this, and now it is growing like this. So this minimum at this is not the global minimum, because this is the, so this, suppose at this point, this value assigned to this is lower than this. So this dy by dx equal to 0 gives me local minima, not a global minima, right? So this is local minima. The same case with the multivariable functions, where I have, instead of curve, I have a surface in 3-dimensional space. So again, at the surface, you have to find del f over del x to be equal to 0. You have to use these relations to find your critical point, where like in curves, you have this maximum, this like maximum, or this either this value or the top of this mountain. Okay. In case of surface, you need to find certain plateau. Plateau in the sense the plane, because this is surface now. This is not a curve now. Okay, so this is some geometrical point of view in multivariable functions to find the critical points. So again, let's not worry about those things, but remember here. So ultimately, you are supposed to find these extremum values of this function f. But now you have to follow this constraint as well. So you cannot go and randomly find the extreme value. If your point x, y, z is maximizing this function, at the same time, it should satisfy this constraint as well. If not, then that cannot be your extremum value or maximum value. So for that, now you have written your Lagrange multiplier or Lagrangian function L. So why we are doing this, and how it can correlate with our original problem. So original problem in which we are extremizing this f. Now in this Lagrange multiplier technique, instead of extremizing this function f, I am going to extremize this Lagrangian function. And how these are same? Now if you look at this del, sorry, if you look at this Lagrangian function, this is a function of x comma y comma z and lambda. So if I need to extremize this particular Lagrangian function, I need to find the critical points, and for the critical points, I need to satisfy how many equations? Now 4 equations. So if you would have extremized function f directly, you would have considered only 3 equations: del f over del x, del f over del y, del f over del z to be equal to 0, but not necessarily only 3, because at the same time you need to follow this constraint, this phi of x comma y comma z to be equal to 0. So ultimately, these 3 equations for f to find critical point, and 1 constraint, you need to solve 4 equations. And now I have written Lagrangian function instead of these 2 functions f and constraint phi, and now I have additional variable. So if I want to find the critical point for this Lagrangian function, I need to satisfy these 4 equations, equal to this over del y equals to this over del z, and this over del lambda as well, equal to 0. Okay, so this we are familiar with. Now look at this particular equation over here. Suppose if I this equal to 0, and if you look at the function form, this f only depends on x comma y comma z. This does not involve lambda, and lambda is involved over here only. So if I differentiate partially with respect to lambda, I get this particular equation, x comma y comma z equal to 0, and this is nothing but my constraint. This is nothing but my constraint. So by writing this in a Lagrangian function form, now I'm able to get the constraint as well. I'm able to satisfy the constraint as well. So that is why we are doing this. It's not like you are not considering the constraint at all. You are considering the constraint, but not as a separate equation to this. You are considering the constraint, but through some different form, just by writing your Lagrangian to be equal to f plus lambda times phi, the constraint. Okay, and now to find the extremum, you need to solve for this, solve these equations. You'll get certain relations. So basically by solving this equation, so you got 4 equations. So you got 4 equations, because this is 1, 2, 3, and 4 equated to 0. You have got 4 equations, and you have got 4 unknowns. You have got 4 unknowns. Which are those 4 unknowns? The value of x, the value of y, z, and the value of Lagrange multiplier as well. So this x, y, z would be the critical point which you'll be looking for. And at the same time, the 4th variable is your Lagrange variable, which will help us to satisfy this constraint phi of x comma y comma z to be equal to 0. So ultimately you got 4 equations and 4 unknowns. You're able to solve these equations. You'll get from this a critical point, and lambda as well. So you'll get 4 unknowns, critical point x, y, z, and your Lagrange multiplier lambda as well. So by solving, we are able to find the value of Lagrange multiplier. So if we use in the function f of x comma y z, this critical point, we are able to find the extremum value of the function. How to find it? Let us take a simple example of this. So you must be familiar with this example. So let me take this simple example. So, okay. So divide, suppose if I take simple, divide 10 into 2 parts such that their product is maximum. Their product is maximum. So I need to divide this 10 into 2 numbers such that their addition is 10 basically, and if I multiply these 2 parts or these 2 numbers, I must get the product to be maximum. So we have solved this in 12th standard. So how do we solve this? So let us take one part to be equal to x and the another part to be equal to y. So the sum of 2 parts must be 10. And now if I denote a new function, let us call this function f of x comma y equals to product of these 2 parts, x comma y. This will give me as, so this y, this x and y, addition of x and y is 10. So I can always write this y in terms of x. So from this I can directly write in explicit form this product of 2 parts as x into y I can write as 10 minus x. So this is basically nothing but 10x minus x square. Now I need to, so this is the product. So this is the g of x is the product and I need to maximize this product. So how to maximize this product? I know g dash of x. Find the g dash of x, this 10 minus 2x. This has to be 0. If you find the x value, so this x is equal to 5. So x equal to 5 basically extremizes this product g of x. But at the same time, I need to find whether it is giving me a maximum or minimum. So for that, we have second derivative test. So this g double dash of x, if you find from this is minus 2. Minus 2 is less than 0. So it means that it is going to maximize this. It is going to maximize this. So this will give x equal to 5 will give me a maximum value. Suppose if x equal to 5, then if x equal to 5, then my y value is also 5. And if I take a maximum product, so maximum product value would be 25. So I have solved this by our standard methodology, x plus y I have written. So from 2 variables, I have come to the single variable problem, and which our standard methodology we studied in 12th. I'm able to find the maximum value of the product. Now, the same problem we are going to solve using Lagrange multiplier technique. Okay, so what is this Lagrange multiplier technique? So let me write this. So I'm going to extremize this function xy because this is my product and this is my constraint, because I need to find the maximum value of this xy, but at the same time, I must follow this constraint. It should not happen that for certain value of x and y, I'm able to get this maximum value of xy, but I'm not able to follow this constraint. This should not happen, right? Okay, so let's solve this by Lagrange multiplier technique. Okay, so in Lagrange multiplier technique, my function f of x comma y, which need to be maximized, is xy. And my constraint phi of x comma y is equal to, so the constraint, let me write this constraint, x plus y equals to 10. So I need to write this like x plus y minus 10 equal to 0. Okay, so from this, you'll define this Lagrange multiplier, Lagrangian function. So these would be the variables x comma y. I have one constraint, so I have one Lagrange multiplier lambda, and I can write this as function original f of x comma y xy plus lambda times x plus y minus 10. Now I'll be extremizing this Lagrangian function. So how to go about this? These variables are x, y, and lambda. So let me find this del L over del x. So from this I get, this is y plus lambda. This is equal to 0 because I'm finding the critical points now. Again, del L over del y. Del L over del y. If I differentiate this, I get x plus lambda equal to 0. So from this I get lambda to be equal to minus y. From this I get lambda to be equal to minus x. And if you look at the third equation, del Lagrangian with respect to del lambda, you get this x plus y minus 10 equal to 0, which is nothing but our constraint. So whenever you differentiate your Lagrangian function with respect to certain Lagrange multiplier, you'll definitely get a constraint assigned to this corresponding Lagrange multiplier. So we are satisfying all these three equations. So among which one is our constraint. So it means that we are going to satisfy this constraint. Okay, so what we have got over here? So we have got the value of x to be minus lambda, the value of y to be minus lambda, and we have a constraint. So on solving these three equations, three equations means like putting x equals to minus lambda, y equals to minus lambda into equation 3. So let me call this equation. This is 1. Let us call this is second. This is 3. So from 1 and 2, I have got the relation for x and y in terms of lambda minus lambda, x equal to minus lambda, y equal to minus lambda. And I'm putting this in third equation, which is nothing but my constraint. So minus x. So this is minus lambda. Again, y? Minus lambda minus 10 equal to 0. So if you find, you get the value of lambda. This value of lambda is equal to minus 5. The value of lambda equal to minus 5. And again from 1 and 2. Now from 1 and 2, if you put this value of lambda minus 5, you get x equal to y equal to 5. X equal to y equal to 5. And now you can find this extremum value. So this extremum value of f of x comma y, which is your xy, so is basically 5 into 5, that is equal to 25. So you are able to find the extremum value f of x comma y. All right. So this is the way in which you are able to solve the Lagrange multiplier. So you can find the extremum value of the function subjected to constraint through Lagrange multiplier technique. So let us take another example of Lagrange multiplier technique in which, okay, let us take another example. Okay, so let us take this example. Suppose you have a temperature field. You have a temperature field T of, suppose consider a three-dimensional space. Consider a three-dimensional space and your temperature T at point x comma y comma z in space is given by 400 x y square z, and subjected to, you have to follow the constraint. You have to basically find the highest temperature on the surface of. So you need to, let me write this as a word problem. So this would be more interesting. Find highest temperature on sphere centered at origin and having radius 1. So this basically, so let us first understand this question. So this T of x comma y comma z gives me the temperature in the entire space. So if you put some values, suppose if you put origin x0, y0, z0, so the origin, at the origin temperature is 0. Likewise, okay, so in space you need to find the highest temperature, but the highest temperature on the sphere, and the sphere is centered at origin and having radius 1. So you cannot go leaving the surface of sphere. So you have to walk on the spherical surface and find the highest temperature position and the value of this highest temperature. You cannot walk away from that spherical surface and say that here temperature is maximum. It should not happen. You have to follow this constraint that you have to walk on the sphere itself. So let me write this. So this is my function to be extremized. And now my constraint, what is my constraint? So let me write the constraint. phi of x comma y comma z is equal to, I have to be on the surface of the sphere. The equation of sphere with center at origin is x square plus y square plus z square equal to r square, which means 1. So I can write this constraint like x square plus y square plus z square minus 1 equal to 0 form, equal to 0 form. So how do you define your Lagrangian function? Lagrangian function you can write as now 400 x y square z plus lambda times your constant. You have a single constant, so you have one Lagrange multiplier, x square plus y square plus z square minus 1. So this is your Lagrangian function. Now your Lagrangian function depends on x, y, z and lambda. So if you differentiate with respect to x first, with respect to x, you have got this equation 400 y square z plus 2 lambda x equal to 0. All right, no worries about that. Second equation, del over del y, you have got this 800. Now you have got xyz from this second term plus 2 lambda y. Again, this has to be equal to 0. The third one, del L over del Z. These give me 400 xy square plus 2 times lambda z equal to 0. And let me write this here, del L over del lambda. This gives me x square plus y square plus z square minus 1 equal to 0. And this is nothing but my constraint. So always if I differentiate with respect to Lagrange multiplier, I'll get the constant itself. Okay, so I have 4 equations now and 4 unknowns x, y, z and lambda, and I need to solve. I can solve these equations, no problem with this, that. Okay, so how to solve your equations? You can always find the value of one of the variable and put into some another variable. Okay, that can be done. So if you put here in this particular, suppose if I put the value of lambda, if I take the value of lambda and put it somewhere, or if you find the value of y, let us say from this, if you find the value of y or lambda, anything, you can find anything. Suppose if I want to eliminate y, you can put the value of this and here, or you can take the value of lambda as well. So if you find the value of lambda here, so you get lambda, you have to divide by 2y. So this is minus 400xz, minus 400xz. So now you have to put this value of lambda in this equation, in this equation, and in this equation. So you don't have any value of lambda over here. You just have x, y, and z here. So basically, if you put the value of lambda here, you get the equation in x, y, and z like that. And you can find and you can solve these particular equations. So solving these 4 equations, so remember this, these are not linear equations. These are not linear 4 equations, because you have square term, you have this term. So remember always, if you have non-linear set of equations, you have to, and if you are able to solve those 4 equations for 4 unknowns, for that you have to use the substitution. So take any variable from any equation, write this variable in the form of remaining variables, put those in the remaining equations, and try to minimize the number of variables, and at the end you'll get only one equation, and you are able to find the value of those all 4 variables. So this is the methodology. So you can eliminate one by one and find the one equation with one unknown and find that value of unknown. So if you solve, I'm not going to solve this over here. You can find the value of x to be 1 by 2, this y to be equal to plus, or because this involves some square roots, squares and all. So that's why this plus minus and z equal to plus minus half. So these are the solution of your these 4 equations, and definitely you are able to find the lambda as well. Lambda you can easily find out from this, which may look like plus or minus 100. Okay, so these are the 4 values of this your unknowns, a critical point. And now if you find the highest temperature, T of x comma y comma z, this would be 400 into x, half, y square again half, and z again half. So this would be 50. So your highest temperature, and this would be the highest temperature subjected to this constraint. So if you walk on the spherical surface centered at origin with radius equal to 1 and try to find the highest temperature sensed by you, that would be equal to 50. So that value would be equal to 50. So this is how you can use the Lagrange multiplier technique when you are supposed to extremize certain function subjected to certain condition or constraints. And remember, if you have many constraints, you have to consider Lagrange, those many Lagrange multiples, Lagrange multipliers equal to your number of constraints. So which we have already looked the generalized form of Lagrangian function. So this is all about Lagrange multiplier method.